All right, everyone. So let's continue here. And we have an example. So it says you take a glass rod that is charged to point plus 5 nanocoulomb by rubbing. So what we want to know here is have electrons been removed from the rod or protons added? Okay. So I'm hoping that at this point here you're already clear on that in terms of when you're charging something, which particles actually are transferring from one object to another. And that is, you know, always sort of like, let's say, one thing, right? In terms of like always the electrons are moving. The protons, not necessarily easy to move around in the first place because remember, they are in the nucleus, they're very closely bound to one another because electrons and protons, they are bound to one another by the electric force. Protons actually bound to one another by a strong nuclear force, which is much stronger force, um, and it's very difficult to remove the protons. So that's why generally we can assume always there are the electrons, especially the ones that are further from the nucleus, are moving from one object to another, and those are the ones responsible for charging the objects. All right, that means the electrons are the ones that are moving from one object to another. The next question is how many electrons then have been removed or protons added? So let's ignore that right now because we know that no protons have been added. But 5 nanocoulomb is our charge. That means we can say, all right, so our charge here is 5 nanocoulomb plus 5 nanocoulomb. That means we're dealing with, extra positive charges. Remember the equation that I gave you, this is then equals to n times, you know, proton charge. That means some n number of protons put together gives you this charge. Again, not because protons were added, but because when you remove electrons, then you have some n number of extra protons, and they give you the charge. And I just simply just calculate the n, which is then q over electric charge for a proton. So then 5 nano stands for 10 to the negative 9 coulomb, and divided by the electric charge for a proton, 1.6 times 10 to the negative 19 coulomb. You can see, right? Coulomb cancels out, and we get as an answer 3.1 times 10 to the 10 protons, basically. That means this many extra protons right now in this charged rod, glass rod, compared to the electrons. All right, here's another example. Suppose you have 1 mole of oxygen gas. How many coulombs of positive charge are contained in the atomic nuclei of this gas? Okay, so you have to be careful with this example because you are given the number of electrons. Basically, the sorry, not, actually we talk about nucleus, so it's actually in terms of protons. That means number of particles. Let's say you're given 1 mole, right, of this gas, and it's an O2 gas. Oxygen, basically, it's a molecule, right? That means one thing you have to understand here is if you take one oxygen gas, right? So let's say just O itself, the one oxygen, if you look at in terms of its nucleus and look at in terms of how many protons you have, and you guys can refer to the periodic table, oxygen has 8 protons. Okay, that means the element is oxygen if it has 8 protons. Okay, that means 8 protons. Okay, but we have O2. That means we have two oxygen atoms put together. That means it's 2 times 8 protons, which means then 16 protons. Each oxygen molecule is then 16 proton. But then we have 1 mole of oxygen molecules. Now, hopefully you guys remember 1 mole is exactly then the Avogadro number of molecules, which is 6.02 times 10 to the 23 molecules. That means that's specifically a number. All right, so that many molecules. Well, then how many, um, let's say, how many coulombs of positive charge are contained? Well, then Q is the total charge, which is, remember, N times your, let's say, charge that you have. All right, so what we have here is, so this is basically charge of your molecule, N is the number of molecules that you have. Well, we have 6.02 times 10 to the 23 molecules, and each molecule has a charge of 16 E. E stands for 1.6 times 10 to the negative 19 coulomb. So calculate everything together. So then the charge that we have is 1.5 times 10 to the 6 coulomb. Okay. Well, this is a very large number of molecules. So that's why we get a really large, you know, uh, you know, value for charge. But this is what we have. That means um, you have to understand that each oxygen has 8 protons, oxygen molecule has 16 protons, and then this is the number of, molecules you have. Put them together, calculate the total amount of charge. All right, here's now another example. Two 1 kilogram masses are 1 meter apart on a frictionless table. Each has plus 1 microcoulomb of charge. All right, that means you have two objects or particles. Both of them are charged to 1 microcoulomb of charge, but they also have mass of 1 kilogram and they're 1 meter apart. Just put it in a coordinate system and we can find what is the magnitude of the electric force on one of them. So put it in a coordinate system like this, put it in a diagram. Remember, you are working with forces. One of the important things about dealing with forces like this is that you want to put them in a coordinate system, organize them, do the free body diagrams and things like that. All right, so then this is what you would, let's say, usually draw. And I highly recommend whenever you're doing the, let's say, recitations and things like that, remember the idea here is to organize your work well. So doing the recitation, doing the exam questions, anything, try to have a coordinate system, try to have a free body diagram, try to do some kind of pictorial diagram. It will always help you. Also help me to understand, to see if you understand it or not. Okay, so then let's say Q1 on the left, Q2 on the right, 1 meter apart. And since just two charges exerting force on one another, I can use Coulomb's, Coulomb's law equation. F12 equals F21 in terms of their magnitude, K Q1 Q2 divided by R squared. Finding the magnitude, so I can say it's 9 times 10 to the 9 times Q1 is 1 times 10 to the negative 6 coulomb. That's what micro stands for. Q2 here is also 1 times 10 to the negative 6 coulomb. Then divided by their separation, 1 meter square. So then if I find then the force that 1 exerts on 2, which is the same strength as 2 exerts on 1, we can then calculate this to be 9 times 10 to the negative 3 newtons. Okay. So that's kind of what we have for part A. That means we calculate using the Newton's, let's say, sorry, Coulomb's law, and make sure that even if one of them was negative, we need to put absolute value. Unit for the length has to be in meters in order for us to put it there and square that, and then just find it in terms of newtons. Part B says, then what is the initial acceleration of each mass if they are released and allowed to move? That means imagine you were holding them, and if you're holding them, they're exerting exerting force on one another, but you're holding them. But as soon as, let's say, you let go of the Q2, for example, well, there is a force acting on it, and what does the force do? It makes the object to accelerate. That means there's going to be acceleration, which is equals to the force over the mass of the object. That means I'm not considering this just this guy over here, Q2. I'm saying that acceleration of 2 is equals to force 2 divided by mass 2. All right, so force 2 is then 9 times 10 to the negative 3 newtons. All right, so by the way, one thing I also should point out that if you look at the force for part A, this was the magnitude. And then you can say that F12 equals 9 times 10 to the negative 3 newtons I hat, where force 2-1 is equals to 9 times 10 to the negative 3 newtons negative I hat. Negative I hat means to the left. All right, so that's why here when I put like I hat, I'm talking about force and magnitude and the direction, and divide by mass, which is 1 kilogram. So we can calculate this to be 9, 9 times 10 to the negative 3 meter per second squared. All right, so, okay. Interesting thing about this type of, problems is to understand that, for example, let's say I wait until this guy gets to, 2 meter apart, let's say Q2, right, gets to do x equals 2 meters. And let's say I want to know how fast it is moving at that instant, assuming that, let's say, for example, it started from rest. Let's say how fast it is moving when it gets from x equals 1 meter to x equals 2 meters. Well, I have calculated force and acceleration, and sometimes it's intuitive, or for students to think that they can say, okay, v final equals v initial plus at using this kinematic equation, or since we're not given technically the time, but we can use this v square, v final square equals v initial square plus 2 times acceleration delta x. So technically this equation, giving the final speed in terms of initial speed, acceleration, and displacement. Well, we have the displacement, we calculated some acceleration, and then the question is, can I use this equation to calculate how fast it's moving at x equals 2 meters? Well, the answer is no. I can't, because using this equation, the kinematic equation, I need to make sure that my acceleration is constant. But it is not constant. Because remember, when this Q2 gets to this point, then the same force that I calculated before doesn't, work here anymore. Why? Because now the distance here is 2 meters, not 1 meter, which means the force is now 1/4 what it was before. Well, if the force is different, then acceleration is different. That means acceleration is not constant. If acceleration is not constant, I cannot use this equation to find the speed. Okay, all those kinematic equations can only be used if you have, constant acceleration. If you don't, you can't use those equations. All right, so now what we're going to do, we're going to make this sort of like, let's say, increase in difficulty of the problem. So first one was just two particles next to one another exert force on one another. Now we have 3-point charges, and I'm going to make this 3-point charges on the same axis. So let's say I have 3-point charges are on x-axis. Q1 equals negative 6 microcoulomb is at x equals negative 3 meters. Q2 equals 4 microcoulomb is at the origin, and Q3 equals negative 6 microcoulomb is at x equals 3 meters. What we want to do then, find the electric force on Q1. That means what I have here is, as you can see from the diagram, right? This free body diagram, I draw my coordinate system, I have my origin, and then I put all those charges their position. X equals negative 3, origin, right? X2 is at the origin, and X3 is at the x equals 3 meters. But then I know one thing, that if I have this, well, Q1 interacts with Q2, they push and pull. Q1 interacts with Q3, they push and pull. Well, Q2 also interacts with Q3, they also push or pull. But here's the thing, the question asks, find the electric force on Q1. That means Q1 is my object of interest, and I can pretty much forget everything but the interaction of Q1 with other particles. That means I don't care about this combination. I don't care what 2 and 3 do to one another. And I don't even care about what 1 does to others. All I want to know is, what is the interaction between Q1 and 2, where the Q1 is the affected party, and Q1 and Q3, where then the force is on Q1 again. That means that's why what I have here is this. I take my Q1 as an object of interest, and then I look at Q1, Q2 combination. Q1 is negative, Q2 is positive. That means there's going to be attractive interaction. That means Q1 going to be pulled toward Q2. And that's why I have this force F21 acting to the right toward Q2 because it's attractive force. If I then look at Q1, Q3 interaction, well, Q1 is negative, Q3 is negative, so they repel. That means Q1 gonna have a repulsive force basically away from Q3, which is then to the left. That means those are, in a way, you can say, right, this is my free body diagram. Two forces to the right, to the left, acting on it. And then one thing I can do here is step one, which is the free body diagram, right, for the Q1. And then what I can do here, I can say, all right, so let's make a table where I'm going to say these are my forces acting. This is x-axis or x component, right? Y components. And what I have here, this is the table of forces acting on Q1. So there's F21 and there's F31. Because I have more than two forces acting on Q1, I need to find the net force. F21 is then a force that is acting to the right, so plus F21. It has no y component. F31 is acting in a negative direction, has no y component. That means when I'm looking in terms of my net force, it has x component, but it doesn't have any y component, so I can just ignore that. That means this should be the second step for all the force calculations, where you're looking and organizing your vectors, your forces. Step three then will be to get the equation for the net force, the one that, right now we have non-zero, which is the x. So this is then equals to F21 minus F31, because I now also took into account the direction of F31. I can also do it in terms of this, right? I can also, like, let's say, write it in terms of, net force is equals to force 2-1 plus force 3-1, and then let's say put the I hats and things like that. But this is pretty much same thing. This one is indicating that we're only looking at the horizontal components or horizontal forces, and F31 is negative because it's pointing to the left. Okay. Now, then from here, I can do the calculation for the net force in X. F21 is K Q1 Q2 over R12 square minus K Q1 Q3 over R13 square, which means that if I calculate the net force, in a way I can see that here I can factor out K and Q1 from both of them. And all I have is that Q2 over R12 square minus Q3 over R13 square. Okay. So then I can finally plug in all the values, 9 times 10 to the 9. Then my Q1 here, remember, all of them are absolute values, right? Make sure that you guys are remembering that. So that means 6 times 10 to the negative 6 Coulomb. Then in the parentheses, I have 4 times 10 to the negative 6 divided by the distance between Q1 and Q2, which is 3 meters. Then minus, again, 6 times 10 to the negative 6 Coulomb. And the negative is not because it's a negative charge, negative because of the direction of that force. And divide by 9 meters square. And if I do this calculation, basically calculate my net force, I'm going to get, let me put it here, so 1.5 times 10 to the negative 2 newtons. And since this is only x component and there is no y component, I can then say, all right, so the force acting on this charge Q1 is just in terms of its x component. So it has 1.5 times 10 to the negative 2 newtons. And since x component is positive, that means it's I hat. There you go. So that's the answer for this example. You can see, right? When you have more than two charges, then you need to calculate the net superposition force, right? So the net force. That means you have to look at all the forces acting on charge of interest in terms of their direction, in terms of their magnitude, right? And then find the net force in terms of, its magnitude and direction. All right, so now let's look at another example. So this is a negative 2 microcoulomb point charge and a 4 microcoulomb point charge are a distance L apart. Where should a third point charge be placed so that the electric force on the third charge is 0? All right, so that means what we have here is this. So let's say we have a coordinate system where I have negative 2 microcoulomb, that let's call this Q1, and 4 microcoulomb, let's call this Q2. And they are L apart. What I can do, I can just say that this is x equals 0, this is x equals L. Simple enough. That means they're L apart. The idea here is this. If I place a third charge, and the third charge then going to be pushed or pulled by Q1 and pushed or pulled by Q2, but I want such that the electric force is 0 on that charge, Q3. That means I need to find where to put Q3 so it's in equilibrium. Forces cancel each other. All right, so you need to be careful with this one. So let's say we have 3 different regions that we can consider. Region 1 between those 2 charges. Let's say region 2 to the right of Q2 and region 3 to the left of Q1. Okay, so let's look at region 1 first. Region 1 assumes that I put Q3 somewhere. It doesn't matter where. So let's say I put Q3 over here. And honestly, it doesn't even matter what is the charge of Q3. It works exactly, same way if it's positive or negative. Because remember, Q1 is negative, so it's a negative charge. Q2 is positive. We know we have this. Let's assume for simplicity, right? Q3 is positive. Okay, so if Q3 is positive, that means if it's positive, there's going to be force acting on it from Q1. There is going to be repulsive, because if this guy is positive, right? Q1 going to attractive, right? Q1 going to attract. That means Q3 going to be attracted. So here's F1 on 3 toward 1. It attracts. Then Q2 and Q3 combination also going to give us force, but this time is repulsive force because Q3 is positive, Q2 is positive, so Q2 going to push Q3 away from it. Well, away from it means that it's in this direction. This is F23. Well, the question is that if I'm adding F13 and adding F23, will I get 0 or not? Well, you can see, right, we cannot get 0 because both those forces are in the same direction. That means this doesn't work anywhere between those charges. That means region 1, I cannot put anywhere this charge 3 that, the forces are 0 or the net force is 0. Because at any time between those 2 charges, both of the forces pointing to the left, so they can never cancel each other. All right. How about then a region 2? So let's look at the region 2. All right, so for region 2, then what I have is this. That means I put the charge, let's say I put the charge somewhere over here. Let's say this is my Q3. All right, so let's see if this will work. Well, force from Q1, again, remember, my Q3 here is positive, right? So Q1 and Q3, they have attractive force. That means the force going to be to the left on Q3 because of the Q1. It's going to attract. It's going to be attracted towards Q1. This is F1 on 3. Okay. This is going to be attracted. Force from Q2, because Q2 positive, Q3 positive, going to be repulsive away from Q2. Well, then here's that force over there. F3 on 1. All right, seems like we're getting there. So F net, right? F1, let's say, like F net, which is then F31 plus F21, sorry, F31, I get this one wrong. This is then 2 exerting on 3. There's, 1 exerting on 3 and 2 exerting. So that means this is the force that 1 exerts on third plus 2 exerts on the third. Can this be then 0? Well, the good thing is they're already in the opposite direction. So that means what I have is this F23 minus F13. So technically, there's a difference. We're not adding them, we're subtracting. The only problem here is this. Q2 is greater than Q1 in magnitude, plus R2, right, the distance between 2 and 3, or R2, 3, is greater, sorry, is smaller than R1, 3. And that makes a big difference. Not only charge 2 is bigger than charge 1, it also always closer to charge 3. That means force 2, 3 always going to be greater than force 1, 3. That means force 1, 3 will never be strong enough to cancel F2, 3. The idea, remember, they have to be either same or, same, right, in order for it to cancel, but it's always going to be smaller and never equal. So unfortunately, this also doesn't work. Basically, that leaves it here to bring Q3 at position, at region 3, and see then what happens. So in region 3, what I have here is this. Q3 going to be pulled toward Q1, as we already know. So it's going to be this, right? Force 1 and 3. Q2 going to be pushing Q3. So the force is going to be in this direction. Force 2 and 3. That means it's already, again, it's nice that they're in opposite directions. So then F net is equals to F1, 3 plus F2, 3. And I can see that F1, 3 is I hat, F2, 3 is negative I hat, so that at least works. That means, there's a possibility of canceling them, right? Also, even though Q2 is greater than Q1, R1, 3 now is smaller than R2, 3. Remember before, R2, 3 was smaller than R1, 3 always. Now R1, 3 is smaller than R2, 3, which allows then F1, 3 at some point to match the value of F2, 3 and to get 0. That means this is where we can actually have this region, right? Where we can have the object to be, let's say, the forces to be same magnitude, opposite direction, that you can cancel them. All right, so then if that's the case, let's do the calculation. Let's see what we get. So in terms of then calculating the position, at least, finding the expression, because we're just given everything in terms of L and, let's say. So here's one thing we can do. Okay. To calculate then the position, I know one thing now, that this is going to be true. That means F1, 3 plus F2, 3 equals 0. But because F2, 3 is to the left, so that means I can say F1, 3 has the same magnitude as F2, 3. Which means then if I'm writing F1, 3, it's going to be K Q1 Q3 divided by the separation between them. And the separation between them is this distance, right? Basically Q3 and negative Q1. So let's call this some distance X. That means they are distance X apart, square that. And this is equal to the force that 2 exerts on 3, which is then K Q1 Q2 exerts on 3. So Q1 Q3 divided by the separation between 2 and 3. Right, I don't need this anymore. So separation between 1 and 3 is this distance here, which is L plus X squared. Okay. Now that means those two are equal to one another. So what I can do is this, K can cancel out, Q3 can cancel out, and this is why I said, right, it doesn't matter what charge is, the test charge. I can just cancel them. And what I end up with here is this, right? So if I cancel those out, then I end up with Q1 over X squared equals Q2 over L plus X squared. Remember, those are absolute values always. And one thing I know here is that this is 2 microcoulomb, this is 4 microcoulomb. That means Q2 is equals to 2 times Q1. That's another thing I know. That means I can come back and say that this is 2 times Q1. And what I can do then from here, for this particular example, I can cancel Q1. And you can always do that, right? Represent one in terms of the other one, like let's say, a ratio. So that means what I end up with is this: 1 over x squared equals then 2 over L plus x squared. What I do here, I cross multiply, then I have L plus x squared equals 2x squared. Okay. If I move 2L squared to the left, and then say that this is equals to 0, so I get 2x squared minus L plus x squared equals 0. I open it up, L plus x squared. What I end up here is this, then x squared minus 2lx minus L squared equals 0. Again, all you have to do is just open it up and just combine them together, and this is what you will get. Which you can see just ends up being a quadratic equation. All we have to do from here is then solve for x. All right, so let me kind of get rid of this. So then continuing here, x will be equals to, using quadratic equation, right? So 2L plus minus square root of 4L square plus 4L square, right? And then this is divided by 2, which gives us x equals L plus minus square root of 2L. Okay. And that will be basically the expression for finding the position where the particle 3 can be, placed and have no force acting, basically be in equilibrium. All right. So let's continue. And here's another example. So this one now is sort of like a two-dimensional calculation for the force. So I have a point charge of 5 microcoulombs on the y-axis at y equals 3 centimeters. And the second point charge is of negative 5 microcoulombs on the y-axis at y equals negative 3 centimeters. That means I have two charges on y-axis. But then find the electric force on a point charge of 2 microcoulomb on the x-axis at x equals 8 centimeters. That means by placing particle 3 on x-axis, now I'm making it two-dimensional. Because what happens here, you can see, right? This is my configuration where I have Q1 and Q2 sitting there, but my Q3 is on the x-axis, and that's my charge of interest, because find the electric force on that Q3. So that means I need to look at Q3 as a charge of interest and all the forces acting on it. Q1 is positive, Q3 is positive, so F13 is a repulsive radial along the radial line, right, away from Q1. That's the force of 1 on 3. Q2 is negative, Q3 is positive, so then it's attracting Q3 toward it along the radial line. Again, you can see it's now toward the, Q2. That means, in a way, this is my, by just sort of like making a local coordinate system, I can see this is X, this is Y, and this is my free body diagram for Q3. It has one force in a fourth quadrant, F13, another force in the third quadrant, F23. Since I'm given this position of Y and X, I can use them to find R, right? And I also can use them to find this theta. Because this is now two-dimensional, which means I need to use the component method. All right, so the step 1 will be to do this free body diagram. Step 2 will be to do the force table. These are my forces. So I have F13, F23. All right. That means my equation is this: net force is equals to F13 plus F23. But I cannot add them just directly to one another because there are, two-dimensional vectors. Vectors, I need to do vector sum. That means the best I can do right now is to find the components of the net force, and then from there to find the, the magnitude and direction of the net force. Okay, that means I have to break all of them down into components. So that's why I have this table where I do that organization of the work. So I can see that first I look at F13. F13 is in the fourth quadrant. So if I take the F13 and I break it down into components, I'm going to get something like this, right? The X component, and then this is the Y component. Remember, parallelogram will allow me to do that. And I can see that the theta is with respect to the X-axis. So F13 basically becomes F13, the X component, right? F13 cosine of theta, and Y component, F13, then sine of theta. Fourth quadrant means X is positive, Y is negative, which you can see from the direction as well. F23 is in the third quadrant, same thing, right? I have then F23 cosine of theta, because theta with respect to negative X-axis, and F23 sine of theta. And negative, negative, because it's third quadrant. And then net force. So this is going to give me the net force in the X direction. The sum of the other two going to give me net force in the Y direction. So force table allows you to organize everything, put the correct directions for the components and things like that. Then step 3, you get two equations. One equation is this guy here, which is to find the net force in the X direction. That means you add everything above it. And everything I have is F13 cosine theta, then minus F23 cosine theta. And then equation 2, net force in the Y direction, which is adding those. Negative F13 sine of theta minus F23 sine of theta. All right, so let's then continue. Let's see what we get here. Well, F13 is K Q1 Q3 over, actually let me do that over here so you guys, so if I'm calculating that, right? So the force that 1 exerts on 3 is K Q1 Q2 over R, let's say 1, 2, sorry, this is 3. So 1, 3 square. I have Q1, right? And I have Q3, which is 2 microcoulomb. That means then I can calculate that. I also have a direction. R is then, R square is then will be X squared plus Y squared, right? So that means I can do that as well. Then what I have here is, for this particular equation, I can see that since Q1 equals to Q2, that means both of them have the same, well, the other one is negative, but let's say, remember in this equation, when I plug in, I'm going to put absolute value and they are equal to one another. And R13 is equals to R23. Both of them have exactly same distance, right? To the, charge 3. Then I can say that this F13 that I calculate is same as basically F23. Now, I can calculate then the theta using this configuration, because I'm given X and I'm given Y. Remember, X is, 8 centimeters, so 0.08 meters. Y is 3 centimeters, so 0.03 meters. So then I can use that to find the theta using inverse tangent. I can find the theta, so 0.03 over 0.08. And let's say then what I can get here is roughly 21, let's say, degrees. And the idea here is that because you have this Y is the same as this Y and X combination, same as for Q1 and Q2, that means theta 1 and theta 2 are also the same, which you can see then if I put it in equation 1 over here, I'm going to get 0 because I get same F12, F13, F23, same cosine thetas, then I get 0, which means that those X components cancel each other. The Y components then add up to one another because those are the same, thetas are the same, so it's basically negative 2, the, let's say Y component than sine of theta. Because the magnitudes are the same, I can just add them. That means it becomes negative 2 times, well, Fy. So if I do this calculation, I plug in into this calculation, I'm going to get 12.32 newtons. And then sine of, which is about 21 degrees, plug in everything, then I'm going to get negative 8.65 newtons. And I can put, like, let's say j hat to indicate that this is just vertical. But actually, this is just a y component. Then I can say then the net force, since the x component is 0, this net force is this negative 8.65 newtons, but it's in a j hat, negative j hat direction only because it has no x component. And that will be then the answer for this example. All right.